I need to be very structured here because I'm used to speaking for longer and sometimes I'll wander off and I'll have to stay on cue. So I'm going to talk about science, which is a bit of a stretch for me. In particular, is whether computing is a science. So first, for those of you who don't know who I am, I have spent most of my career looking at languages, learning about them, trying to move tech forward. I always loved the higher level languages. And since about 2009, I've also been working on discovering better organizational structures. And you probably might know this book or these books. I was also 8 years on the C++ Standards Committee from the beginning. And some other books and other books. A lot of C++ stuff at first. Co-authored a book on the Flex language, and then Steve Jobs kind of spiked that. I mean, arguably Adobe also spiked it. And later, much too late, they open sourced it. But by then, that train had left the station. This is one of my more recent books on the Scala language. And that book is now being translated by Svetlana Isakova, who works at JetBrains, which is creating the Kotlin language. So I'll be learning this language by editing her translation, but not, I won't have to figure it out myself. I'm basically the editor and the publisher of this one. Not sure when that'll be done, but, and I've been working on this for the last couple of years just because people kept asking me when was I going to, update Thinking in Java or do another Java book. So I was just going to do something really quick and dirty, and then 2 years later, it's now almost done. I used to write for these things called magazines and conferences, and I used to be involved with a conference called the Software Development Conference. Used to be a big deal, and then the internet came along and they didn't know what to do with it, even though they were in the software industry, so they just kind of augured into the ground. Then, I don't know, maybe 15 years ago, I started organizing my own conferences, small ones. And so eventually we started creating the Java Posse Roundup, which is an all open spaces, self-organized conference. And then a few years ago, the Java Posse decided that they didn't want to do Java anymore. So we changed it to the Winter Tech Forum. And so this is my town of Crested Butte, Colorado. And right now, probably more snow than that is what you're seeing. But so we have the Winter Tech Forum, and it's coming up just in a couple weeks. So, and I'm planning on doing one in the summer. I'm hoping this summer to start doing it on Python concurrency. The other thing that I've recently started doing just in the last year is a thing called developer retreats. It was an idea that occurred to me, which is, so the open spaces conferences are very low structure. Basically, we have a board on the wall and people put Post-it notes in for discussions that they want to have, and then they meet and have discussions. So I don't pre-organize anything, and it works amazingly well. But I started wondering, well, what would happen if we just took away all the structure altogether? But that would be too crazy, and I couldn't do that. And then a couple of people who come to these other conferences said, hey, you know what I'd really like? And they said exactly the same thing. So we started having these things, and it's just a small group of us, typically in my living room, and we usually work on some sort of theme. And it works remarkably well, and people like it. So we're doing another one on the Elm programming language that's happening right after the Winter Tech Forum. And one of the things that I'm trying to do is build an app, which will be an open source app, that creates open spaces board instead of having to have the paper one. Well, it'll be in the cloud, so you'll be able to use it and post to it and everything from handheld devices. That's been something I've been wanting to do for a while. So through all this, all these different languages and everything, ever since I discovered Python, which was, I don't remember when I discovered it, it was, long time ago, it's rapidly became my favorite language, and I kept refusing the call. But, and this, some of you may have seen me wearing the shirt yesterday. I created this shirt for the 2009 Python conference. And my favorite language and community is Python. And so my next project, which I've actually started, is Concurrent Python. So this will be an intermediate to advanced level book on concurrency in Python. And you can find, it's under my GitHub, you can find the first couple of chapters. It'll be, the ebook will be free. People say they want a print book, and so eventually I'll probably do that if that persists. But the idea is the ebook will stay free. I don't know what license I'm going to use, but anyway. The other thing that I've been working on since around 2009, you can find at reinventingbusiness.com. And this is a big project. That's why I have Mount Everest here. Everybody's got their own personal Everest to climb. And you may not have discovered yours. And usually when you discover it, your first thought is, that's too big, I could never do that, and you turn away from it. And I did this a lot in my life. I saw the problems in how we work, how we organize, and I just thought, well, that's too big, and this is the way things are. There's no way I could change it. But in 2009, I started working, researching, didn't know where it was going to take me, and eventually things are starting to go some very interesting places. And I write about this on this blog, reinventingbusiness.com. So that's kind of everything. Now I want to get to the topic, which is what is science and is computing a science? And my friend Zach, he jokes that if you have to call it a science, it's probably not a science. So if we look at the different sciences, like pure math, well, they don't call themselves a science, but nothing happens in the world nothing happens in the math world, but we have equations that are self-referential and they have consistency. This is from Saturday morning breakfast cereal. Whereas with chemistry, there's all kinds of things that happen, but when I say we don't have equations for them, I mean that you can't say yet, you can't say, oh, well, if we put these molecules together, we'll get this effect. I mean, we have a bunch of other equations for like when titration happens, et cetera, but all kinds of things happen. But we are yet to be able to predict what chemicals we can put together and what kind of effect they will have. But I think that's going to happen, and then we'll see yet another amazing set of things happen in the world. Physics, things do happen in the world, and we have equations for some of them. That's kind of the whole point of physics. Social science, people do things. We sort of imagine there might be equations. You'll recognize some of these things from XKCD. It's, I'm being flippant. They actually have more progress than that. But the joke was probably about political science. Yeah, there's no science in political science. Psychology, things happen. How do you feel about them? There's some really old rocks. Some anthropology looks at people who do and think differently than us. Is that a science? Well, it's probably observational. They can come up with maybe some predictions. I don't know enough about anthropology. Yeah. So I'm sort of oversimplifying a bit. Philosophy, we're using our thinker to think about how we think, and and engineers and philosophers just, that we don't get what their questions don't make any sense to us. Okay, and in biology, even though biology seems very observational, but they do have 4 fundamental theories. Everything is made from cells. Genes carry information. The heredity happens, and there's such a thing as evolution. And those are the cornerstone theories of biology. Economics is an interesting one. There's a fair amount of argument about whether economics is a science. Economists will often say, well, look, we've got mathematical equations, therefore it's a science. But their equations come from pretty much made up stuff, and you end up with things like, I don't know if people remember the Laffer curve, which says that the lower you make taxes, the more the economy benefits, and George W. Bush, or no, H.W. Bush referred to it as voodoo economics, which it actually is. But some people would argue that all economics is voodoo economics. But there is another kind of thing which is more recent called behavioral economics. And here, we're looking first, instead of saying, gee, the way people should work in the abstract is how I imagine it in my head. I have a story in my head, let's make an equation, and then let's say that that equation is giving us meaningful data. With behavioral economics, it starts with, what are people actually doing, and now can we detect some patterns from that? Okay, that I have some hope for. That's, whether it's science in the traditional sense, it's certainly not economics in the traditional sense, but it's something that actually seems to be producing viable results, whereas traditional economics is still, even economists will admit that it is not a science. And then there's management science. And this is definitely, this is a hot button for me because of my studies of organizational structure. And the father of management science is, if anybody remembers the story, Cheaper by the Dozen. This guy lived around the early 1900s or late 1800s, and he's famous for basically making up data and then fudging the data and then taking the conclusions from that made-up fudged data and say that it means something. So management science is precisely the opposite of science. But what came out of this was a bunch of people that said that, oh, well, look what this guy did and he got rich, so I'll do the same thing. And if you remember, there are books like In Search of Excellence. I don't know if people remember this book. Yeah, it made a huge impact. So In Search of Excellence, what they did is they sat down, a couple guys sat down at their kitchen table and they say, what makes companies excellent? That would sound good in a book. And so they came up with 7 things that sound really good. And they said, what companies do our thing? So they came up with some companies that seem to follow their principles. And they say, we'll say that the reason those companies are successful is because they did our thing. And so this is completely backwards thinking. But they sold tons of books, so they got rich. Therefore, the science in management science is really about how to fool people into thinking that you understand management. You can turn the knobs and make the profits go up. So really huge amount of expletives involved in this. And then now we're getting a little closer to what we're doing. With engineering, very practical, says there's some things you can do and you will probably get some good results and build things. Very practical, very pragmatic. And now we're to computer science. So computer science, we have a kind of a fantasy novel because it's all made up. I mean, we made everything up. We made all the decisions. We invented the world. Probably why a lot of people in computer science are really into fantasy games and everything. And compared to normal science, all these other sciences, at least, they looked at things that were happening in the world or that might happen in the world, and they tried to come up with a set of rules so that they could maybe fit what they'd seen and predict things in the future. But in computer science, we invent the rules. Like, for example, we decide that zeros and ones are the numbers that we're going to use, and we decide that, what the thresholds are. So even down to the hardware, we made those decisions. And then as we get higher and higher, we created the languages. And so we try different languages and we invent them and we pretend that they're wonderfully designed or not. On and on and on. And so that's what makes it kind of weird to think about as a science, is because it's all invented out of our head. However, when you're looking at languages, it does seem that over time, as we create multiple different languages, we begin to discover that certain rule sets seem to work better than others. So for example, we might start to realize that, instead of having variables, invariants seem to cause seem to take away a set of problems that we have when we have variables. Things like that. You know, that's why this resurgence of functional languages. It solves a set of problems. So some rule sets seem to work better than others, and that might be the science in computer science. Even though we're making it up, if we make up a whole bunch of different worlds, we discover that some seem to work better than others for some definition of work better. Also, it seems like one of the things that we've started to do is discover things about the development process that should be singular to see if there's anything useful in that. And this is kind of like anthropology and behavioral economics do. It's not what we normally think about as computer science, but it is actually very practical for what we're doing in the process of building applications. So, what is a scientific theory? This is something that a lot of people get confused about. And it's really, it starts with a hypothesis, which is, I wonder if this might work. The hypothesis has to be testable. So we have to do some experiments to either verify or show that it's not true. And the experiments must be replicable. So if I do something, if I say, hey, I've discovered cold fusion, and I did this one experiment and I seem to get some electricity out of it. A bunch of other people have to be able to do that experiment and either get the same results or not get the same results. And that way we check each other's work. So you begin with the hypothesis, and then basically what you try and do is knock it down. You try and disprove it. And other scientists also try and disprove it. And if it lasts, sometimes you run into people who say, I don't like that idea, and so it shouldn't work, or it's obviously wrong, but they don't want to do the work to knock it down. It doesn't fit with their beliefs or the way that they want to see the world. That happens, but that's not science. So the thing is, if this hypothesis doesn't get knocked down after a period of time, it might actually be a theory. And so one of the core ideas of science is that it isn't about fact. It's not, we like to say, oh, well, science has shown these facts, but scientists really don't think in terms of facts. They think in terms of process. They say, well, I have an idea, it might fit the data, it might be predictive, but I'm not going to say that it's true or not true. All I'm going to do is say that it fits data and it predicts the future. So the foundation of science is curiosity. Here's a nice XKCD. He pulls the thing, he gets zapped by lightning. A normal person might say, I shouldn't do that. The scientist says, I wonder if that happens every time. That's the difference, because the scientist is curious. So that's kind of what we do as computer scientists. We get some results, we look at them, and we go, gee, I wonder if I put this kind of team together, and this, the more anthropological way of looking at it, this is how we came up with the idea of pair programming. We go, it's interesting, let's put people together and see what happens. And after a while, we say, well, they don't seem to be writing code as fast, but the quality of the code seems to be better. Okay, that's a science, I'd say. So when I started looking at this, and I should give you a little bit of background, my undergraduate degree was in physics. I spent a little time with journalism, and then I changed to physics, and then I started adding engineering on top of it. But technically, my degree was in physics, but I had no idea I did not understand science at all. I just thought, there's equations. And my problem was that I thought the equations represented some kind of truth. And only in the last 10 or 15 years did this all kind of start coming together for me. And I realized, they're just a model. And so I was looking for certainty in science. And it's not about certainty, it's the opposite of certainty. If you want certainty, that's belief. Belief, oddly enough, gives you certainty, even though it requires faith. Whereas science is all about doubt. With science, we doubt everything. You say that you found a faster algorithm, and my first thought is, I'll bet you haven't. I will try and prove that you haven't. Scientists doubt in the face of all supporting evidence. We say, well, yeah, so far your model seems to support that evidence, but I still open the possibility that maybe that model is wrong, and the model might be restricting us from thinking about something bigger. I mean, maybe the reason we don't have anti-gravity yet is because our model is preventing us from thinking a particular way. And that happens, I think, in computer science as well. So all we're doing as scientists is we find a model that fits the evidence. And this was the thing that I couldn't figure out when I was studying physics. I thought the equations represent some kind of truth. But we're just trying to fit the evidence. And thus, a theory is simply a model of the world. And one of the great phrases when people were talking about modeling initially that someone whispered in my ear is, all models are wrong, some are useful. And that's stuck with me forever because it allows you to put that thing in perspective. You don't believe in the truth of the model. It's, the map is not the territory, that kind of thinking. So with a theory, you never prove it true. There is no, and this can be very disturbing to people who want to believe that science gives us truth. You never prove a theory true. It simply fits the data. And they used to call them laws. So there was Bernoulli's law and the second law of thermodynamics, et cetera. But that was in the early part of the scientific revolution where they thought, yes, we have discovered truths. We don't really call things laws anymore. We just call them theories. And of course, when people want to attack theories, they go, well, it's just a theory. What they're really saying is if they say just a, they mean just a hypothesis. That's just an idea that you've got in your head, but you don't have any data backing it. Whereas a theory, you have data backing it. It's like, yes, it's just a theory. Every time we have tried this theory, it hasn't been disproven. But of course, it can be disproven in the future. So to be valid, any theory must be falsifiable. So we have to, when you create a theory, there has to be some way to prove that it's wrong. You can never prove that it's true, but you have to be able to prove that it's wrong. So circular reasoning doesn't work. If you say, well, there's all kinds of possibilities for circular reasoning, and I can't think of anything off the top of my head that isn't religious, so I'm just not going to go there. Anyway, that doesn't work because there's no way to prove it wrong. So, for example, here's a hypothesis that I came up with that might work in anthropology. I'll say that stories which are presented as allegory, so I'm telling you a story, but it's not true. Now, the only reason I'm telling you that story is to inspire you. Whereas stories that are, this is my hypothesis, stories that are presented as this is the truth are intended to control. So if I'm saying, well, this is the truth, then I'm trying to get you to do something, not to inspire you. So we might go out, if I were an anthropologist, I might go out and study different stories in different cultures and see which ones were allegories and which ones were presented as truth, trying to support or debunk my idea. And then if I were able to say support it, I might suggest that if a culture has a story which has outrageous magic in it that we clearly know is not true on a day-to-day basis, then that story was not to be believed, but instead to ensure that it could only be used as inspiration. So that's the kind of conclusion I might be able to draw starting from that hypothesis if I was able to support it. I have no idea whether that's true, but right now it's making sense in my head. Okay, so when we get closer to hard science, sometimes this theory can be expressed as an equation. But that's just some way of describing a model. And the equation, just like any model, has to fit the data and it has to be predictive. But this was the thing that bothered me, is that I always expected an equation to make sense. And in physics, they often do exactly that. They go, well, let's make a hypothesis about how something works, we'll put in a factor for that, and then if there are variations, we'll put in additional factors for those. And so I always thought all equations had to make that kind of sense. In fact, another XKCD thing says, this guy's a physicist, and he says, well, just model it as this simple object. You know, you're trying to model the way the specific heat of an object works. And you could say, well, let's assume that molecules are billiard balls connected by springs, and then add some extra terms for variations. For any kind of complications, we'll just throw on some extra terms. So it's easy. And that's how it's often done in physics, but then that's just because that's the way they have traditionally done it, and that is kind of, our thought is inherently limited to that kind of thing. We think in stories. And so this guy can make up a story and produce an equation for it. But now we've got machine learning, which creates these equations and algorithms that make no sense at all to our minds. They're just a pile of stuff, but they work. They fit the data and they're predictive. So we couldn't, you know, a physicist is not going to be able to come up with an equation that describes what a particular type of flower looks like. But machine learning can do that. It can create this thing, and it's a big, messy equation that we can't comprehend. But it can be uploaded into your phone, and your phone can look at this flower and say, oh yeah, that's one of these kinds of flowers. So that's very different, but it's still science because it creates this model. Solving one of these equations is often some discovered trick, such as the so-called vibrating drumhead problem in physics. If it vibrates around it, so it's a circular drumhead, and you start it vibrating, and it has these different waves, and you can describe the equation, but to solve it, there's this thing called a Bessel function, which I still don't thoroughly understand, but some guy looked at the equation and he said, well, I think this will, you can plug in the place from the center of the drum and what time it is, and this will tell you where that drumhead is, how it's vibrating. And there's a bunch of equations in physics that are like this. It's just somebody had some wild insight. It wasn't algebra that they worked out, but it works. So again, all right, it's still science. Now in programming, we have developer tests. We usually do developer tests based on problems that we either suspect or we have actually encountered, but these aren't, and if the test fails, that means your code is broken. But it's not generally what we think of as falsifiability tests in science. Concurrency in most languages. Now, some languages, pure functional languages, because they're starting from first principles to be friendly to concurrency, those, it's possible to create things where you can, it might be possible to prove that they're working correctly, at least under some conditions. But in most languages, including Java, including Python, C++, most of the languages that we work with, we have no way, well, yes, that's true. We don't have a falsifiability test that we can do. The only thing is, sometimes you can discover situations where it's broken, but that doesn't show you whether it's working in other cases or not. In other words, the problem with concurrency is that you can write a program that you believe to be true, and it can have hidden bugs in it. And there's no way to prove that that bug exists other than it appears occasionally. It's a very messy situation. So this is a big one. Tests are still kind of, I mean, if you think about it, they're experiments, and as long as the experiments keep exceeding your hypothesis, which is my code is somehow okay, is supported. But this isn't very satisfying. We can peek behind the curtain. We can find flaws in our own hypotheses using inspection. So that's different than a lot of other situations in science, because we know what's going on underneath the covers. As I mentioned, pure functional languages have a certain appeal to them because they follow some math-like rules. For example, in a pure functional language, everything is invariant. You have no variables. So there's no possibility that you're going to have two tasks that step on each other's toes, because if a value can't change, then nobody can change it and have the other person uncertain what that value is. So making everything invariant allows us to be certain about that. Functions being stateless and having no side effects allows us a certain degree of reliability. And then composition between functions. If we have two functions we know are correct, we can compose them and create a third function we know are correct. But even with this, it's still possible to have issues of deadlock, and you can write a concurrent system that only works under certain conditions but can be overloaded. So it's not a perfect world, but at least a pure functional language gets us much further into reliable systems. Okay, I'm going to skip that one. All right, so what kind of science-y things do we do in computing? We invent and learn about machines and languages. That's, I'd say, a science-y thing. We try stuff out and we see what sort of results that we get, including what sort of machines might work better than others and what sort of languages might work better than others, and characteristics of these. We are also able to explore things that we can do with computers that we were never able to do with mathematical equations. So all kinds of numerical methods, which it was simply impossible. I mean, unless you had, I suppose if you put everybody in the country to work doing numerical methods, it might be possible to do without a computer, but just let's call that impractical. And then something that I'm particularly interested in now is studying ways that people work together. And I think for some reason, maybe it's because it's so easy to put together a company around software, and it's also very easy for such a company to go away, we seem to be iterating this kind of thing faster and faster, and we're able to learn more and ideally say, hey, this kind of team works better, or this kind of structure works better. And ultimately, we're trying to figure out how to make better software faster. And so at least we have a goal. We have something that we're able to say, well, this team might do that and that team might not. And of course, there's all sorts of human variables that make this difficult, but the fact that we're able to iterate faster and explore more ideas faster, I think will get us. And I feel like, well, this goes back to my reinventing business explorations. I think that we're very close to finding a structure that is going to cause explosive creativity and growth and value creation. So I have high hopes for that and hope to be involved in that. So here's something, we always say seeing is believing, but in science, seeing is not believing. In fact, if you believe without seeing something, that makes you a believer. But scientists see things and they go, well, yes, it might fit the model, but I don't believe or don't believe it. I just agree that it fits the model. So this is zombie Fineman. And Richard Fineman is a famous physicist. And he says, ideas are tested by experiment. That's it. That's the whole key of science. Everything else is bookkeeping. So a scientist doesn't believe anything, and they're skeptical of everything, but which is a little bit of an adjustment that you have to make if you're not, and it certainly was for me, if you're not used to thinking of things that way. It's kind of unsettling at first, but eventually it's liberating. Once you get used to thinking that way, it's actually very liberating. And you're not spending your time trying to decide whether you believe something or not. You're simply saying, I observe this. And when you see a new problem, you don't say, does this fit with my belief or does it apply to my beliefs? You simply start fresh. And in Zen, they refer to this as beginner's mind. And that's it. So I think, do I have a few minutes to take questions? If there are any questions? And of course, I didn't say whether computer science was or wasn't a science, but I just wanted to create a conversation around that.